By 2050, the world population is estimated to reach 9 billion, with 70% of all people living in cities. As countries develop, there'll be an ever-increasing demand for building materials needed for housing as well as energy and transport infrastructure. Concrete is the ideal material to meet many of the challenges the world will face in the coming decades. It is low carbon, made from abundant resources, fire resistant, makes buildings more energy efficient, and is extremely durable. It's widely used for architectural structures, foundations, walls, pavements, bridges, roads, runways, dams and reservoirs. It's used to make furniture and even in ships. Concrete is a mixture of cement, water and aggregates. Different types of cement have been used for thousands of years, but the most common cement used today is Portland cement, invented in the 19th century and based on heating a mixture of finely ground limestone and clay that hardens when water is added.
Concrete still is a very low CO2 material in itself. The reason why we talk about such huge volumes, 5% of man-made CO2 emission, is purely the amount of concrete used worldwide.
Continuous innovation in both cement and concrete over the past decades have improved its performance and reduced the impact of their production on the environment. However, just like buildings, research into the nano and micro scale of cement and concrete needs foundations. That is what we do. We do fundamental research into the microscale phenomena that govern the performance of cements and concrete.
Cement is continually evolving, it's continually changing its composition slightly. And so we need to be aware of how these slight changes in composition are going to affect subsequent behaviour. So you need to ensure that the materials that are being used now are going to perform adequately over a 50 or 100-year lifetime.
Nanocem is a consortium of European academic and industrial partners. Working together, we combine passion with pragmatism, cooperation with independence, and long-term vision with hands-on experience. We don't develop products directly, but the combined academic and industrial knowledge that we produce drives the development of new and improved materials and products that are adapted to modern needs, whilst minimizing the environmental impact of the construction cycle.
I'm very happy with the way Nanocem has turned out as an organization where you really do have good balance between the industrial need and the academic interests. Every year we make our cements more efficiently, and the concretes we make from those cements are also designed more efficiently so that we reduce wastage and reduce emissions in proportion.
Our aims are to grow the basic knowledge needed to develop new cementitious materials, to link features and processes that take place at atomic level and their impact once used in buildings, bridges or other structures. We aim to disseminate the results of our work and prepare the next generation of researchers by educating university graduates and providing a platform for future employment in the cement and concrete industry, as well as help find solutions that will reduce the environmental impact of cement and concrete. We do this by organizing workshops and seminars, sponsoring research in multi-partner projects, acting as a recruitment base for researchers in cementitious materials, highlighting the importance of R&D at the European level, and acting as a networking body ensuring academic research is relevant.
The game has changed, and it's changed as a result of being able to talk to the other academics from other aspects of cement science, material science, and bringing an alignment between what we can do, the problems, and the end users, and that really has been very beneficial.
Our research does not focus on finding a revolutionary type of new cement, but rather on making concrete even better. We study cement and concrete at a microscopic level to help understand the scope of physical and chemical reactions that occur when using different cement types or materials in the concrete mix. Furthermore, we look at how the concrete is likely to perform in the future. Fundamental research is needed to study these complex materials and their interaction with the environment that surrounds them. Our research supports several parallel pathways of reducing concrete's carbon impact, including improved prediction of performance of new types of cement and concrete, research into the performance of different mixtures, as well as looking into the performance that different cement types with alternative materials have today and might have over time.
Progress we've made in understanding the fundamentals in the last 10 years makes it clear that we can solve these problems.
Many of our current research projects are studying some of the most exciting fields in the development of cement and concrete. Our research aims to better understand these materials, to reduce the need for resources and lower emissions, whilst making concrete more durable and stronger.